Hello, welcome back to the lecture series in wave optics. In last few lectures, we have discussed about the Fresnel class diffraction. In the last lecture, we have started discussing Fraunhofer diffraction at a single slit. Today, this lecture will be the continuation of the last lecture, that is the Fraunhofer diffraction at a single slit. In last lecture, we have discussed a plane monochromatic wavefront is incidenting on a single slit and passing through it and spreading towards the screen, and on the screen we will be getting alternate dark or bright region. At the center you can see we are getting a high intense point, and that we just called it as central maxima. Here the intensity will be maximum, and above and both sides of the central maxima we will be getting alternate dark and bright region with less intensity. With we will be getting the this maxima here, the intensity is less in comparison with the central maxima. So this maxima we just called it as secondary maxima. Well, this was the picture we have discussed. This was the pictorial representation of the single slit diffraction. Here we have the source of light. We are considering a slit as a source of light, and that slit is perpendicular to the plane. Therefore, we will be getting a cylindrical wavefront that is incidenting on the lens, and the lens will make it a plane wavefront. That plane wavefront is incidenting on this slit, and we consider the slit width as E. Now, those light without any deviation, those wavefront through the slit AB without any deviation, that will be focusing at point O, and at the point O we will be getting the central maxima. Now, we have discussed the condition for the principal or central maxima, that is the path difference shall be 0, and that path difference shall be 0 at the point theta is equal to 0. That point corresponds to the central point O. Now, those light which deviate by an angle theta, that will be focusing at point P. Now, if theta changes, the point P will be changes. So, therefore, P is an arbitrary point on the screen, and we took D is the distance between screen and the slit. Now, we will continue this lecture as position. What is the position of the minima or darkness? We have derived in last lecture that what is the resultant intensity at a point P on the screen due to the diffraction through the single slit. That is, the resultant intensity I is equal to I0 into sin alpha divided by alpha all square, where alpha is pi e sin theta divided by lambda, where lambda is the wavelength of the light and theta is the angle of diffraction and E is the slit width. Now, we know that at minima or a dark point or darkness, the resultant intensity shall be 0. Now, in the equation of that resultant intensity I0 into sin alpha divided by alpha all square, I0 shall not be 0 because I0 is the intensity of the central maxima. Then the possibility is the second term sin alpha by alpha shall be 0. So, in this case alpha cannot be 0. If alpha is 0, then we will be having theta is equal to 0 from this equation. Therefore, theta is equal to 0 or alpha is equal to 0, that will be giving the condition, or that will be giving the position of the central maxima. Therefore, the possibility for the formation of the minima is sin alpha shall be 0. So, if sin alpha is equal to 0, then alpha shall be plus or minus m pi. I am just substituting the value of alpha here. Alpha is pi e sin theta divided by lambda, that is equal to plus or minus m pi, where m is equal to 1, 2, 3, 4 etc. Here m is not 0. Why it is? If m is equal to 0, this condition shall be E sin theta is equal to 0. that will be leading to the condition that theta is equal to 0, that is the condition for the central maxima. Therefore, here m is not is equal to 0. So, if you cancel out this pi and pi from here, you will be getting the condition for the minima, that is E sin theta is equal to plus or minus m lambda. So, this is the condition for the minima, this is the condition for the formation of minima or darkness in case of single slit diffraction. Now, let us see how we can find the position of the secondary maxima. We know that the equation for resultant intensity we have derived, it is I0 into sin alpha divided by alpha all square. Now, if you draw the intensity pattern, the intensity pattern is something like this. So, we have the central maxima at the point O on the screen, at the central point. On both sides of the central maxima we will be getting the secondary maximas and minimas like this. Now, we know that at the maximum point, the derivative of this intensity with respect to alpha shall be 0. That means the slope at that particular point is 0. Therefore, I am differentiating this intensity term here, the intensity term di with respect to alpha. So, I am just substituting the value of I here, d by d alpha of I0 into sin alpha divided by alpha all square, and that shall be essentially 0 at the maximum point. So, if I am differentiating this, we will be getting I0 into differentiating like 2 sin alpha divided by alpha, 2 into sin alpha divided by alpha, and again differentiating with respect to alpha, which will be giving you alpha into cos alpha minus sin alpha all divided by alpha square, and that is again essentially equal to 0. If this condition need to be, if it is satisfying like is equal to 0, then either this term or the term inside the bracket shall be 0. If sin alpha divided by alpha is equal to 0, that will obviously leading to the condition of the formation of the secondary central maxima. Therefore, the term alpha cos alpha minus sin alpha shall be 0 to satisfy this particular equation. If I am rearranging this, we can have alpha on the one hand side, alpha cos alpha is equal to sin alpha, and sin alpha divided by cos alpha will be giving us the alpha is equal to tan alpha. Now, what I am doing here now, we are drawing two graphs. One is y is equal to alpha graph, and another graph y is equal to tan alpha graph. If I am drawing the graph of y is equal to lambda, that obviously will be providing as a straight line. So, this graph is y is equal to alpha graph, and we are taking here it is plus pi, here it is 2 pi, here it is 3 pi, and so on. On the left hand side, here it is obviously we will have pi, 2 pi, 3 pi, etc. Now, if I draw the graph of y is equal to tan alpha, that will be giving another type of graph. So, at the 0 point tan alpha shall be 0 and it increases like this, and here also we will be getting, and again tan alpha is 0 at pi, then it increases, and here it is increases, and we will be getting different graph at 2 pi, 3 pi, etc. Similarly, we will be getting on the this negative axis as well. Now, we know that in the last slide we know that the position of the secondary maxima will be forming when alpha is equal to tan alpha. That means these two, wherever these two graphs are getting intersect, here it is intersecting, here the both graphs are getting intersect, here it is intersecting, here it is intersecting. So, these are the intersecting points. So, at these intersecting points we will be getting the condition for the formation of the secondary maxima. So, let us see where these points are getting intersect. First it is intersecting at point 0, then in between this minus pi and pi there is no anywhere it is intersecting, and then the first intersection we can find, the second intersection we can find in between pi and 2 pi, and this point will be 3 pi by 2 point. Similarly, here in between 2 pi and 3 pi there is an intersecting point, and that shall be 5 pi by 2. This is 5 pi by 2, and so on. So, this intersecting point satisfy this alpha is equal to tan alpha. Let us see what are the point of the intersections are. Here alpha is that both graphs are getting intersect when alpha is equal to 0, 3 pi by 2, 5 pi by 2 and 7 pi by 2, etc. And obviously we know that when alpha is equal to 0, this condition leads to the formation of the central maxima or principal maxima. Therefore, we can omit that one. The remaining will be the position of the secondary maxima. So, at the center point alpha is equal to 0, we will be getting the maximum intensity. Now, the next intersecting point which is at 3 pi by 2, there you will be getting the first secondary maxima. Here it is 3 pi by 2, here we will be getting the first secondary maxima, and at 5 pi by 2 another intersection point, correspondingly you will be getting the second secondary maxima. Here it is the intersecting point, here you will be getting the second secondary maximas, and so on. So, in generally this is 3, 5, 7, these are the odd numbers. So, you can write it as 2n pi by 2, where there is no 0.5 pi by 2. Therefore, you can write this formula as alpha is equal to 2n plus 1 pi by 2, where n is equal to 1, 2, 3, 4, etc. Here n is not 0 because we are not having any 0.5 by 2 or 1 by 2 pi we do not have from this form values. Therefore, we do not have the n is equal to 0. So, we will be getting the position of the secondary maxima when alpha is equal to 2n plus 1 pi by 2, and I am substituting the value of alpha here. Here you know that alpha, the value of alpha is pi e sin theta divided by lambda, that will be giving you plus that will be equal to 2n plus 1 pi by 2, and the pi and pi will be getting cancelled out from here, and then this condition is e sin theta is equal to 2n plus 1 lambda by 2. So, this is a condition for the formation of the secondary maxima in case of a single slit diffraction. Now, let us see how the intensity distribution graph. Again, now we are starting with the resultant intensity equation, I is equal to I0 sin alpha divided by alpha all square, and we know that the intensity of the principal maxima in the last lecture we have already been discussed, that the intensity of principal maxima is I0. Therefore, the maximum point here it is I0. Here I am plotting on y axis as intensity, and x axis we are plotting it is alpha or theta, you may just have that value. We are plotting it as alpha. Now, the first secondary maximum shall be forming at 3 pi by 2. Then at 3 pi by 2 you can calculate the intensity. So, if I am substituting the value of alpha 3 pi by 2, and here it is again if I am substituting the value of alpha as 3 pi by 2, that will be giving an equation I is equal to 4 by 9 pi square into I0. That is obviously it is I0 divided by 22, that is the approximate, that is about 4.5 percentage of the maximum intensity I0. That means the first secondary maximum here we shall have the 4.5 percentage of the maximum value. So, the secondary maximum, the intensity shall be lower in comparison, smaller in comparison with the maximum intensity. And if I am taking the second secondary maximum, the value of alpha is 5 pi by 2, and again substituting here sin alpha divided by alpha all square, then we will be getting the intensity as 4 by 25 pi square into I0, and that shall be I0 divided by 62, that will be essentially 1.6 percentage of the maximum intensity. Again the intensity is decreasing like this. So, this is the intensity decrement in case of in case of intensity distribution graph of the diffraction pattern obtained from the single slit. Now, let us see what is the width of this central maxima. Now, we are considering the slit here. Slit we took it as E, and the light is spreading out, and intensity pattern formed on the screen. We have the central maxima like this, and both sides of the central maxima we will be getting the minima, and the next to the central maxima we will be getting the first minima. Here this is the position of the first minima, and again this is also the position of the first minima. Let us take the distance x. Now, x is the distance of the distance between the center of the central maxima and the first minima. Then obviously the width of the central maxima is 2x. So, this distance from here, this distance shall be the width of the central maxima, x plus x, that will be giving us 2x. So, let us see how to have the equation for that central width of central maxima. So, we are taking a right angle triangle from here. So, this is the theta, and here this is also theta. So, I am taking sin theta. So, sin theta is x by d, opposite side divided by the hypotenuse. I am taking it as d, the distance between source and screen. If the distance is large, so this distance is approximately equal to the capital D itself. Now, if we are placing this lens very close to the slit, then we have, you know, that this is here this distance is the focal length of the lens. If the lens is very close to the slit, then D can be approximated as f. Therefore, I can write this equation as x by f itself. So, we have the equation for sin theta from the from this diagram, and again the first minima, the condition for the first minima, we will be taking the value of m as, we know that the equation is E sin theta is equal to plus or minus m lambda. So, for the first minima, the value of m will be taken as 1. So, E sin theta is equal to plus or minus 1 lambda, and simply sin theta shall be equal to plus or minus lambda by E, and here from this equation, equation number 1, we have the sin theta is equal to x by f, and I am substituting the value of x by f over here, and then obviously we can easily find the value of x is equal to lambda into f divided by E, and if we know the value of x, then the width of the central maxima can be easily be calculated, that is 2x is equal to 2 into lambda f by E. So, this will be the width of the central maxima, and again this width of central maxima 2x is directly proportional to the lambda, which means that width will be more for the red light and the less and it is less for violet light, and 2x, the width of the central maxima, is again inversely proportional to the slit width. That means the slit width will be greater for the narrow slit. Here it is the intensity distribution graph of the diffraction pattern formed on the screen due to diffraction from the single slit, and this graph is drawn by using a GeoGebra software, and you can see the central maxima here, and both sides of the central maxima we have the secondary maxima, and then we have the secondary minima as well. And let us check how the intensity pattern varies with changing the wavelength as well as the width of the slit. Now, let us see, this is the way let us check how this intensity pattern vary with the wavelength. So, if we decrease the wavelength, you see the intensity pattern, the width of the central maxima becomes narrower. Now, what happens if the slit width, here it is giving giving the slit width variation. See here, if we increase the slit width, you can find out how the width is varying. if the slit width I am increasing, then obviously the width of the slit decreases gradually. Well, so I hope you understood how the slit width, how the width of the central maxima varies with the slit width and wavelength. Let us exemplify this case with the slit width as 6 into 10 raised to minus 4 centimeter and the wavelength we are taking it as 6000 angstrom. Then what will be the width of the central maxima? So, the condition for the first minima is E sin theta is equal to 1 lambda, and sin theta can be written as lambda by E. So, if we substitute the wavelength and the width of the slit, and we will be getting it is the value, it is 0.1, and correspondingly we will be getting the theta value as 5 degree 44 minutes. Now, we will be having the theta on one side. So, this is a formation, sorry, this is how the formation of the central maxima, here this is the central maxima region. So, this angle is theta, that we have theta 1 over here. Then the complete angular, if we are taking the complete angular width, this shall be like this. So, here there is another theta 1 angle. So, total angular width of the central maxima shall be 2 theta 1. So, 2 theta 1 shall be 11 degree 28 minutes. If you know the width of the screen and slit capital D value or the focal length of the convex lens you used, you can easily find the linear width of the central maxima as well. See here another case, if we have a single slit with a slit width as 0.4 millimeter, and the screen it is at a distance 2 meter away, and we are measuring the distance of the second dark band. It is 1.6 centimeter from the middle of the central bright band. Then what shall be the wavelength of light? So, we are taking the second dark band. Second dark band means which will be like this. This is the central maxima. Then we have the secondary minimas on both sides. So, this is the second secondary minima. This is the second secondary minima. Well, we are considering the slit over here. Now, this angle shall be theta 2. Let me take it as, because it is we are taking for the second minima. Yeah, this is the second minima. This is the second minima. Here it is second minima, theta 2. Here you can find sin theta 2 as sin theta 2 usually be small value, that shall be simply equal to theta 2, and that shall be equal to this distance. Let me take this distance as y, and then the distance between source and screen as capital D. The values are given, it is y by capital D. Similarly, we are finding the condition for the second secondary minima. Therefore, that is the condition here, it is E sin theta 2 is equal to plus or minus m lambda was there for second secondary minima, that will be 2 lambda. Therefore, sin theta 2 or approximately equal to theta 2, that will be giving you 2 lambda divided by E, and this will be equal to the equation number 1. Here it is also equation for theta 2. So, we have lambda y by d. So, 2 lambda divided by E is equal to y by d, and if you substitute the value of y, d and E, which all are given in this particular case, you will be getting the wavelength as lambda is equal to somewhat it is 5600 angstrom. Well, now we will move to the diffraction at a circular aperture. Supposed to be a circular aperture, a small circular hole through which the light is passing, and when it is passing through this hole or circular aperture and falling on a screen, then we can observe a pattern like this, and at the center you can find a maxima, then after that maxima you can find a minima here, then we can find another maxima of with diminishing intensity, and so on. We will be finding diminishing secondary these maximas with a smaller intensity or intensity is called the secondary maxima here. Now let us discuss how this pattern form. So this is the pictorial diagram to explain the theory of the formation of diffraction from the circular aperture, and here we are considering a circular aperture. Essentially this is a three-dimensional view we required it, and this is here AB is the slit, and we are taking it as the D is the diameter of that circular aperture. Sorry, AB is a circular aperture and D is the diameter. Now those light without any deviation is focusing directly on point P, and those light wavefront which is deviating by an angle theta, which are focusing at a point P1. And let us take the distance between P and P1 is x here. So obviously those light without any deviations are focusing at point P, therefore PE will be the position of the central maximum. Now in order to calculate the intensity equation for intensity at point P1, we have to calculate what is the path difference. Path difference of the light wavefront reaching at point P1. So let essentially we are taking a point A and B, which are the two extreme point of that circular aperture. Now A and so the light wavefront, secondary wavefront from A reaching at point P1, the secondary wavefront from B also reaching at point P1, and they are superposing with each other. Therefore we have to calculate the path difference. So from D to P1 and from B to P1 is equal path, then obviously this distance, the AD shall be the path difference, and if this angle is theta, obviously this angle also this particular angle also shall be theta. Then you can easily calculate AD as D sin theta, where D is the diameter of the circular aperture. So P1 will be the minimum intensity if the path difference D sin theta is equal to n lambda. If this condition satisfies, we will be getting the minimum intensity or darkness, and if this path difference D sin theta is equal to 2n minus 1 lambda by 2, then we will be getting the condition for maxima, or that means the P1 will be the maximum intensity. So we have to imagine that a three-dimensional view of that circular aperture. Now when it is passing in the last picture, supposed to be this point is a minimum point. So P1 to this is a distance, P to P1 is x, and if we are considering supposed to be the length of this pen is supposed to be x distance, in a three-dimensional view you can find this in a circle. So therefore the minima formed in a circle. So this is how the pattern it is forming. So minima formed in a circular pattern. Therefore we are getting the circular rings here. So a central region with maxima that is look like a disc, then we obtain a next minimum a ring of minima or darkness, then we get the minima of secondary maximum, and so on. So obviously this pattern look like a circular in structure, and the central disc is called Airy's disc, and this one is the this maximum disc, the maximum intensity disc, we just called it as Airy's disc. Now this Airy's disc is surrounded by the alternate dark and bright concentric ring. These are called Airy's ring. Now the intensity of the dark ring is 0 and the intensity of bright ring decreases gradually when we move away from the center of the Airy's ring. Now what is the width of that, what is the diameter of the first minimum ring? Let us calculate it by this formula, where here let us have sin theta is equal to x by f. If I am having the screen over here and from center, now this is supposed to be theta and supposed to be here it is forming the minima, then obviously is this distance is x. Do not confuse with the above diagram. The above diagram x we have taken in downward direction, here we have taken in the upward direction. So, sin theta is equal to x by f, and the first minima formed when E sin theta is equal to 1 lambda, that will be giving sin theta is equal to lambda by E. From these two equations, so this is equation number 2. From these two equations we can have x1 by f is equal to lambda by E, where you can find the radius of the first circular first ring of minimum intensity as lambda by EF, where but in Airy's assumptions the radius of the first minimum ring, it is slightly greater than lambda by EF, that he has according to Airy he has concluded that the radius of the first minimum shall be 1.22 of into lambda by EF. So, with this I am summarizing today's lecture here. We have discussed the Fraunhofer diffraction at a single slit, then we have discussed the conditions for minimas, secondary maximas and central maxima as well, and we have drawn the intensity profile, and then we have discussed how the diffraction taking place at a circular aperture and how the Airy's disk and Airy's rings are forming. I hope you could follow my session here. With this I am ending. Thank you.